Evaporation exceeds precipitation in the subtropical anticyclone belts. So the regional distribution of moisture flux has been analyzed through back trajectory analysis for 1958 to 2001 by Gemamal, and others. A global summary for June, July, August, and December, January, February is presented. Here it shows that the North Atlantic provides moisture for precipitation in eastern North America, Central America, and North and South America during June, July, August, while in December, January, and February. So it's DJF. It also provides moisture to Europe, North Africa, and Central South America. The Western Pacific warm pool provides moisture for precipitation over Central and Northern South America. The North Pacific and South Pacific sources provides moisture for precipitation over the latitudinal extremes of North and South America, particularly in the respective hemispheric winters. The sources are numerous for the Indian Ocean region. In December, February, four sources, the largest spanning most of the ocean between Australia and South Africa. One over the Juho-Hess Current, so over the Zanzibar current and one in the Arabian Sea provide moisture for surrounding continental areas of the African continent and the Arabian Peninsula. In June, July, August, the monsoon circulation make these four areas into moisture sources for precipitation over the Indian Peninsula. In December, January, February, the Mediterranean and the Red Sea provide moisture for areas to their northeast. Finally, during June, July, August, there are sources over the Gulf of Mexico for the southern and eastern United States, in the Coral Sea, and over subtropical South America. In general, the patterns reflect the role of warm conveyor belts over the mid-latitude oceans and the systems of low-level jets in the Americas east of the Cordilleras, the southerly jet over the high plains of the United States in summer. Air masses. An air mass is a large volume of air with particular temperature and moisture conditions that tends to be relatively homogeneous in the horizontal direction over a wide area. Torbjörn in Sweden developed the concept in the 1920s. At low level in the atmosphere, an air mass tends to take on the characteristics of its underlying surface: snow cover, warm cold ocean, moist dry, and hot cold land. The primary source regions for air masses shown in this figure are the snow-covered northern continent in winter, continental polar, continental polar air, or CP air, the subtropical ocean, maritime tropical or MT air, and the tropical deserts, continental tropical or CT air. So CT air right here, and also in Arizona. Near the ground, CP air is cold, dry, and stable. CT air is hot, dry, and unstable, while MT air is warm, moist, and stable. M like marine, so you have water here. And CT air is dry and hot. So, as it is moving over colder surfaces, for some purposes, Arctic air MA and CA may be defined in high southern latitudes in winter with a corresponding Antarctica. Antarctica type in high southern latitudes. Continental and Arctic air is very cold, dry, and stable. In winter, in its source region over the Arctic Ocean. In summer, it is replaced by maritime Arctic air due to the melting snow and ice surface and increasingly the greater open water area due to shrinking sea ice cover. Near the equator, the ocean air mass is designed as equatorial maritime, which is hot and humid with generally unstable air. The mid-latitude oceans are indicated to have a maritime polar or MP air. So in this figure, you can see, so this is a secondary air mass formed by the modification of CP air as it flows out of the continent over a warmer ocean surface and evaporates warm water from the surface, becoming moist and unstable due to surface heating. Notice that CP, CT, and MT air masses all form in areas of high pressure where the air movement is slow, so that the air mass has at least 5 to 7 days to develop its characteristics. As air masses travel away from their source region, they tend to lose their distinguishing characteristics. Frontal zones. So frontal zones from between constructing air masses, especially polar and tropical air. The term front was developed in Norway during World War I as an analogy to the battle fronts in Europe. Air streams with different characteristics converge along an extensive boundary or frontal zone. The primary zone is the polar front between MT and CP or MP air. The polar front is located in middle latitudes, shifting between about 30 degrees north in the North Atlantic in winter and 60 degrees north in summer. So as this figure shows, in summer there is an additional Arctic there is an additional Arctic frontal zone located near the Arctic coastlines of Eurasia and Alaska. It is contributed to the thermal contrast between the cold Arctic Ocean, overlaid by shallow, cold Arctic air, and the snow-free tundra overlain by warmer CP air, but differences in general in energy budget between the tundra and boreal forest may be a supplementary factor. In the southern hemisphere, the polar front is more zonal and represents the transition zone between cold polar easterlies and mild mid-latitude westerlies. Frontal zones are also known as baroclinic zones, where pressure and density surfaces intersect in a vertical cross-section of the atmosphere. This is in contrast to air masses, which are essentially barotropic, where pressure and density surfaces are parallel to one another with height. Baroclinic zones give rise to jet streams in the upper troposphere, and these tend to steer the movement of low pressure system. And this figure shows the atmospheric fronts over the globe as identified by an object analysis as the average of 4 independent reanalysis data sets for 1989 to 2009. High frontal frequencies of the order 10% of the time are located in the extratropical storm tracks in the North Atlantic, North Pacific, and Southern oceans. There are high frequencies close to high terrain, especially at high latitudes. For example, east of the Canadian Rocky Mountains, subtropical frequency maxima are evident near the South Pacific Convergence Zone. And near Taiwan, the Western Pacific. Analysis of rainfall associated with fronts shows that the southern hemisphere 20% of rainfall is associated with both warm and cold fronts and 11% with quasi-stationary fronts. Corresponding values in the northern hemisphere are 17, 14, and 11%, respectively. Precipitation over the oceanic storm tracks is mostly associated with cold fronts, up to 42% for the North Atlantic, while over the northern hemisphere continents it is mainly associated with warm fronts, 30 to 58% over North America. In the northern hemisphere, there are strong seasonal variations with smaller percentages in summer. The southern hemisphere has much fewer seasonal variations. For mid-latitudes 30 to 60 degrees south, the figures are 29, 28, and 11% for warm, cold, and quasi-stationary fronts, respectively. Between the northerly trade wind system of the northern hemisphere and the southeasterly system of the southern hemisphere, there is a zone of convergence known as the intertropical convergence zone, ITCZ. Convergence has two components, the confluence of two merging air streams and a speed convergence where the flow slows down and so air piles up. These two components may reinforce one another or cancel each other out. Similarly, divergence may consist of flow defluence and or speed divergence where flow accelerates downstream. Convergence divergence at the surface leads to rising, sinking air and cloudiness, clear skies. Convergence in the ITCZ is not continuous in time or space because intermittently or locally. The trades are weak, notably in the regions known as the doldrums in the eastern equatorial oceans. These regions were much feared by sailors in the days of sailing ships as vessels were becalmed there and ships could become stranded for long periods. In the 1930s to 1940s, the ITCZ was termed the intertropical front, but although sometimes air mass contrasts may exist over land areas, the zone lacks the characteristics of mid-latitude frontal baroclinic zones. Subsequently, the term equatorial trough has been preferred since it is descriptive rather than implying a mode of genesis. Nevertheless, the ITCZ is usually well developed across most of the Pacific and Atlantic Oceans. Satellite cloud studies show that convergence gives rise to cloud clusters a few hundred kilometers wide forming along the ITCZ.